Welcome to Study Loop.
Okay, so since the inlet velocity is very low, that means the inlet's stagnation pressure should be equal to the inlet pressure, which is equal to 1 megapascal. And the inlet's stagnation temperature should be equal to the inlet temperature, which is equal to 300 Kelvin. So now we can set up such equation here, which is T01 over T1 is equal to 1 plus K minus 1 over 2 times MA squared. T1 here is the temperature before the shock. If we do some arrangement here, we have T1 is equal to T01 over 1 plus K minus 1 over 2 times MA squared. So we know T01 is 300 Kelvin, K is 1.4 because it's air, and Mach number is given as 2.4. If we plug in back to the equation, we have the temperature before the shock is about 139.4 Kelvin. And then we can set a such equation for the pressure. So we know P1 is the pressure before the shock. If we do some arrangement here, we have P1 is equal to P01 over T01 over T1 times, to the power of K over K minus 1. We know the inlet stagnation pressure is given as 1 megapascal. If we plug in back to the equation, eventually we have the P1, which is the pressure before the shock, is equal to 0.0684 megapascal. So now let's determine the pressure after the shock, which is P2 here. So now let's plug in back to the equation. So we have P2 is equal to 6.5533 times 0.0684 Pascal. And this will give us P2, which is the pressure after the shock, is about 448. You know what? Let's write it in the megapascal first. Sorry, this unit here should be megapascal. So megapascal. So it's equal to 0.448 megapascal, which is 448 kilopascal. And the relationship I found between the pressure before the shock and after the shock is based on table A33 for the Mach number equal to 2.4. Okay? And then if you continue looking at the table A33 and then at Mach number 2.4, you'll find the relationship of the temperature after the shock and the temperature before the shock. So if T2 over T1 is equal to 2.0403. And we know T2 can be expressed as 2.0403 T1. So we know T1 is 139.4 Kelvin. So now we can plug in back to the equation to determine the temperature after the shock, which is equal to 2.0403 and then times 139.4 Kelvin. And this will give us the temperature after the shock is about 284 Kelvin. So now let's take a look at the Mach number after the shock. If you take a look at the table A33, so since we know MA1 is 2.4, so therefore the Mach number after the shock, which is the MA2, should be equal to 0.5231. And then we can determine the velocity of the shock, which is equal to Mach 2 times square root kRT2. So we know the gas constant is 0.287 kilojoule per kilogram times Kelvin for the air. So now let's plug in back to the equation to determine the velocity, which is equal to 0.5231 multiplied by square root 1.4 times 0.287 kilojoule per kilogram times Kelvin, and then times 284 Kelvin. And now let's convert to meter square per second square since it's under square root. So it's equal to 1,000 meter square per second square over 1 kilojoule per kilogram. And this will give us the velocity after the shock is about 100 477 meters per second. So now let's take a look at the stagnation pressure after the shock, which is P02 here. So P02 can be equal to P2 times 1 plus K minus 1 over 2 times MA2 squared to the power of K over K minus 1. So we know MA2 is 0.5231, P2 is 448 kilopascal. So now let's plug in back to the equation to determine the stagnation pressure after the shock, which is equal to 448 kilopascal multiplied by 1 plus 1.4 minus 1 over 2, and then times MA2 squared, which is 0.5231 squared, and then to the power of 1.4 over 1.4 minus 1. And this will give us the stagnation pressure after the shock is about 540 kilopascal. And these are the answers for this question.